Hey everyone, welcome back to the channel. Today we are going to understand how large language models or LLMs actually work by building our very own mini GPT. Now, if you have ever heard of GPT-3, GPT-4 or other AI text generators and wondered how does it actually predict the next word, this video is exactly for you. Large language models might sound intimidating at first. They are often described as massive neural networks trained on billions of words, capable of writing essays, generating code, or even composing poetry. But at their core, the concept is actually pretty simple. These models learn patterns in sequence of words and then use those patterns to predict the next word in a sentence. Think of it like a really advanced autocomplete on your phone. But instead of just suggesting the next word, it can generate entire story, poem, or code snippet. Now, instead of diving straight into the complexities of GPT-3 or GPT-4, which requires tons of computational power, we are going to build a miniature version of GPT. This mini GPT will work with a tiny dataset of poems, and it will help you visualize exactly what happens inside LLM. You will see how words are turned into numbers, how the model understands sequences, and how it predicts the next word. By the end of this project, you will not only have a working mini GPT model, but you will also understand the fundamental building blocks of language models, embeddings, transformers, attention, and sequence prediction. In this video, we'll cover three main parts. First, we'll pre-process our data, taking a set of poems, breaking them down into words, and creating a vocabulary that the model can understand. This is where we turn the text into numbers, which is how the neural network read words. Next, we'll build the mini GPT model itself. This is a small transformer-based network that can predict the next word given a sequence of previous words. I'll explain each part of the model, the embeddings, the positional encodings, the transformer layer, and the final prediction layer in a way that is easy to understand, even if you are new to deep learning. Finally, we'll train the model and generate text. You will get to see it create short poetic lines from starting words or phrases, and you will understand how even a tiny model can learn patterns in language. By the end of this video, you will not only have a fully functional mini GPT that generates poems, but you will also have a clear mental understanding of how large language models actually work behind the scenes. You will realize that despite the hype around GPT-3 or ChatGPT, the underlying idea is all about sequences, patterns, and prediction. And that's the power of machine learning. It can turn massive amounts of data into something creative, coherent, and surprisingly human like. So, before we jump right into training our mini GPT model, let's start from the absolute beginning, setting up our project. Because if you are building your own small LLM, even a tiny one like this, the foundation matters. The first thing we do is to create a brand new project folder. Inside this folder, we create the essential Python files we need, a train.py file for training our model, and later a interface.py or terminal script to actually use the model and generate poems. This keeps everything organized from the very start. Once the files are ready, the next step is to download all the required libraries. For this project, the main hero is PyTorch because that's the deep learning framework we use to build the transformer model. Along with that, we use basic Python libraries like OS, random, and math. But the most important installation is definitely PyTorch. So, when you start the project, just open your terminal or command prompt and run the PyTorch installation command pip install torch. This is the system command, or you can use specific commands for CPU and GPU installations. The only thing that takes a moment, and once PyTorch is installed, you are ready to start coding your own mini LLM. After that, we are fully set up. We have our project folder, our training script created, and our libraries installed. And from here, the fun part begins writing the code that teaches our mini GPT how to understand text, learn patterns, and eventually generate poetry. Open train.py and write the following code. Step 1, importing libraries. Import torch, import torch.nn as nn, import torch.optimum as optimum. These lines import the PyTorch framework, which is the backbone of our model. Torch provides the core tensor operations and computational graphs. Torch.nn contains the pre-built neural network components like the layers, embeddings, and loss functions. Torch.optimum include optimizers such as Adam, which will update the model weights during training. These three imports together will allow us to build and train and optimize our mini GPT model. Step 2. Loading and pre-parsing the dataset. Here the code opens your poetry dataset, poems.txt, and reads it into a string. Using .lower ensures all the text is converted to lowercase, which helps standardize the data. For example, sun in capital letters and sun in small letters are treated the same token. Standardizing the text is important for small datasets because repeated variations of the same word could otherwise confuse the model. Step 3. Word tokenization and vocabulary creation. This part converts the text into a list of words using dot split. Each word is considered a token. Set words remove duplicates to create a vocabulary of unique words, which is then sorted for consistency. The vocabulary size is the total number of unique words, which will determine the output dimension of our model, since each predicted token corresponds to a word in this vocabulary. Two dictionaries are created: STOI string to index maps each word to a unique integer. This allows the model to work with numbers instead of strings. ITOS index to string maps indices back to words, which is necessary for converting the model prediction back into readable text. Step 4. Encoding and decoding functions. Encode converts a list of words into a tensor of integer indices, which can feed into a neural network. Decode does the reverse, turning predicted indices back into a string. This function bridges the gap between human readable text and model readable numeric data. Step 5. Hyperparameters. These variables define how the model will be trained and structured. Sequence length determines how many words are input to the model at a time. This is important because the transformer needs a fixed length of sequence. Embedding dimensions is the size of the word embeddings. Higher dimension will allow more expressive word representation. Num heads specifies the number of attention heads in each transformer layer, enabling the model to attend to different positions in the sequence. Num layers is the number of stacked transformer encoder layers which allow the model to capture more complex patterns. LR is the learning rate, controlling how much the weights are updated during each step. EPOS indicates how many training iterations will occur. Step 6. Preparing training data. Tokens equal to encode words. This encodes the entire dataset into a tensor of integer word indices. This tensor will serve as the source of sequences for training. Get batch randomly selects the sequence of word X and its corresponding target sequence Y. Y is the offset of one word so that the model learns to predict the next word at each position. Dot unsqueeze 0 adds a batch dimension since PyTorch model expect inputs in batch size and sequence length format. Step 7. Creating the Mini GPT model. The Mini GPT class defines a transformer based next word predictor. Self.embed converts word indices into dense vectors or embeddings. Self.pause adds positional embeddings, which tells the model the order of words since transformers have no innate sense of sequence order. Encoder layer is a single transformer encoder with multi-head attention. Self.transform stacks multiple encoder layers to capture deeper patterns. Self.fc maps the outer embeddings to vocabulary size logits for prediction. The forward method defines the computation. Create a tensor of position indices for positional embeddings. Some word embeddings and positional embeddings pass through the transformer layer. Apply the linear layer to get logits for each word in the sequence, representing the probability of each word in the vocabulary being the next word. Step 8, Model, Optimizer and Loss. Initializes the model, uses the Adam optimizer for gradient descent, uses cross-entropy loss to measure the difference between predicted probabilities and true word indices, which is standard for classification problems over a vocabulary. Step 9, Training Loop. Randomly samples the sequence X and target Y for each epoch. Computes the forward pass through the model to get logits. Logits.view -1 vocab size flattens the batch and sequence dimensions so cross entropy loss can be applied. Backpropagates the loss and updates the model weight. Every 200 epochs. Prints the current loss to monitor the training progress. Step 10. Saving the model. Saves a checkpoint containing model weights, state dictionary, vocabulary mappings, STOI and ITOS, vocabulary size, vocab size. This file can later be loaded for interface in the interface.py without retraining. Print training complete model saved as poem.gpt.path prints the confirmation that the training is finished and the model is saved. Open interface.py and write the following code. Step 1. Importing libraries. Import torch, import torch.nn as nn, import sys, import os. Torch and torch.nn provide the PyTorch tensors and neural network functionality. Sys allows you to exit the program gracefully with sys.exit. OS is used to clear the terminal screen for a need interface. Step 2. Loading the trained model. Torch.load loads your previously saved model checkpoint. Map location equals to CPU ensures that the model can be loaded even without a GPU. The checkpoint contains STOI dictionary mapping words to indices, ITOS dictionary mapping indices back to words, and vocab size total number of unique words. These are needed for encoding input words and decoding model predictions. Step 3. Defining model hyperparameters. These values must match the words used during training, otherwise, the model weights won't fit. They define the transformer architecture, sequence length, embedding size, number of attention heads, and the number of transformer layers. Step 4. Defining the MiniGPT class. MiniGPT is a decoder-only transformer-like model. Self.embed converts word indices into dense vectors. Self.pause adds positional embeddings so that the model knows the order of words. Self.transformer stacked encoded layers with self-attention, capturing context of all words. Self.fc linear layer that maps embeddings to vocabulary logics for prediction. In forward, positional indices are created for sequence length. Word embeddings and positional embeddings are termed. The sequence is passed through the transformer layer. Logits are returned for every word position, representing probabilities over the vocabulary. Step 5. Loading model weights. Model equal to MiniGPT model.load state dictionary checkpoint model state model.eval creates an instance of the MiniGPT, loads the train weights from the checkpoint. Model.eval sets the model to evaluation mode, which disables dropout and other training only layers. Step 6. Helper function. Encode converts a list of words into tensor IDs using STOI. Decode converts the model predictions indices back into readable words. STOI.get WO uses 0 as a fallback for unknown words. Step 7. Text generation function. Takes a starting phrase string and splits it into words, converts the word to tensor IDs, and adds a batch dimension. For each word to generate, trim the sequence if it is longer than the sequence length, sliding window. Feed the input into the model to get logits. Take the logits of the last word in the sequence. Apply softmax to convert logits to probabilities. Samples a word using torch dot multinomial, introducing randomness for more creative outputs, appends the predicted word to the sequence, and updates the input IDs with the new sequence. Return join tokens returns the generated sequence as a single string. Step 8. Terminal interface. Clears the terminal screen for a clean interface. Prints a decorative header with emojis and borders. Provide user instructions. Step 9. Main loop for interaction. Continuously prompts the user for a starting phrase, typing quit, exit the program, calls the generate to produce a new poem, capitalizes the first word, and ensures that the poem ends with punctuation like dot, exclamation, and question mark for readability. Prints the generated poem in a neat format with double quotes and an emoji for style. So, what happened in interface.py is that it loads the trained Mini GPT model and vocabulary, provides a helper function to encode, decode words, and generate new words in sequence, implements a terminal based interface that lets the user type a starting word or phrase and generate a short poetic line, formats it nicely, and repeats until the user exits. Alright, so once our Mini GPT model is trained, now we are going to run it inside the terminal. You will see a clean interface with the title Mini GPT Poem Generator and their title instruction telling you that all you have to do is type a starting phrase and the model will generate a one line poem based on it. And of course, if you type quit, the program will exit. So let me show you how it works. First, I type rain as a starting word and instantly the model generates a poetic line for me. Rain sings softly in the night sky, hides a thousand secrets. This is all created by the mini GPT we just trained. Next, let's try another one. I type mountains, and the model responds with mountains breathe beneath the moon, stitches light leaks from the ocean. You can see how it forms abstract, poetic imaginary completely on its own. Let's try one more. I type dreams, and again it generates a unique line. Dreams awaken when silence becomes kind of soft petals fall like dreams. Every time we run it, the poem will be little different because the model samples words based on probability. And finally, I type quit. The program politely exits and says exiting goodbye. So the whole interface is powered by a tiny LLM we just built. From loading the model, generating words one by one, and formatting the results, all inside a simple terminal. And the coolest part is, you have just seen a custom GPT style model generate original poetry using nothing but Python and PyTorch.